now we switch to the important subject of process synchronization. Well, yeah, so for the assignment, we need to know about synchronization first. So because we need to synchronize the threads properly. So when you have multiple threads running in parallel and performing certain tasks, you will need to synchronize them correctly to make sure that they will to ensure the consistency of shared data, and also to make sure that you're getting the right results. So there are basically two fundamental reasons for doing synchronization, or two fundamentally different types of synchronization problems. The first kind of synchronization problem is the critical section or the base condition type of problem, where you have multiple threads or multiple processes accessing some shared data, and you want to make sure that the data is consistent and these processes are not causing conflicts or creating conflicts or conflicting with each other or giving or accessing or undoing each other's work, as we will see in the example in a minute. The other kind of synchronization problems is dependency, where when one process depends or needs the results of another process. By the way, in synchronization, all the synchronization concepts here apply to multiple processes or multiple threads. So same concepts. Same concepts apply to multi-processing, multiple processes, or multiple threads. Same concepts. So that's why I will be using the words process and thread interchangeably in the context of synchronization. We know that a thread is different from a process. It's a lightweight process, but in the context of synchronization, the concepts are the same. Okay, so now we will get to understand why we did not fill the buffer completely in the producer-consumer problem. In the producer, in the solution that we have described so far for the producer-consumer problem, if the buffer size is 100, we were filling only 99. So when there are 99 items in the buffer, we consider that full. And many of you were wondering why we were doing that. Now we will attempt to fill the buffer completely and see what happens. See what issues and what problems we will be facing. So let's look at this nice solution, or at least candidate solution to this problem, where we just introduce a variable, a shared variable that we call counter. Counter, it counts the number of items that have been produced but have not been consumed yet. So number of items that have been produced but have not been consumed yet. Which means that counter must be incremented by the producer. So the producer will increment counter, and the consumer will decrement counter. And in this case, our conditions for full and empty are going to be straightforward. Full means counter equals buffer size. If the counter is equal to the buffer size, then the buffer is full, and then the producer must wait. Then the producer will do the production, and it will increment the in a circular manner. Then it will increment counter. Then on the consumer side, the condition for empty is very simple. Counter equals 0. When counter equals 0, then the number of items that have been produced but have not been consumed is 0. So if counter is 0, the consumer is going to wait, and then the consumer will do the consumption as we did before, and then it will decrement counter. Now, This seems to be a very simple, intuitive, and straightforward solution. So what's the problem with this? Well, the problem with this is that we have two processes accessing a shared variable, which is counting. And these two processes may be attempting to modify this shared variable at the same time. So here, there's nothing that is preventing the producer and the consumer from trying to modify this at the same time. Remember that whenever we have two processes running in parallel, we can never make any assumption about the relative speed. So we can never assume that, when this consumer is trying to decrement this, the producer is doing something else. We cannot make this assumption. The producer could be trying to increment the counter at the same time that the consumer is trying to decrement the counter. So let's look more closely into what may happen if both are trying to modify this counter at the same time. Now the key ideas here are incrementation and decrementation. When you increment counter plus plus. So this is one line of code in a high-level language. High-level language. This one line of code in a high-level language will typically get translated by a compiler into multiple machine-level instructions, because this is incrementing a variable in memory. And on many machines, you cannot perform this arithmetic on a variable in memory by one instruction. On many machines, you will need to load counter from memory into a register, then increment the register, then what? Store. So this is machine code. Then store counter, store register into counter. Okay. Now, so this one line statement in a high-level language will get, or in general, may get translated into multiple machine instructions. And now, since we cannot make any assumption about relative speed, and we don't know when a process may get interrupted. So a process may get interrupted anytime. An interrupt can happen at any time. So the interrupt may happen here, or it may happen here, or here. We don't know. So we should write our code such that the interrupt can occur at any point in the code, and we want to make sure that everything will work correctly. Now, if we don't do this, this is what we may get. Let's assume that producer and consumer we have a single CPU. If we have a single CPU, then assuming that the value of counter is initially 5, the producer may load counter, so it will load 5 into a register. Then it will increment register to 6. Now the value of the register is 6. Now at this point, what's the value of counter in memory? Still 5. We haven't updated memory yet. But now what if the producer gets interrupted at this point and the CPU is given to the consumer? Right? So if the CPU is given to the consumer, now the consumer is going to load. It's going to load a 5. It's not going to load a 6. Because in memory, it's still a 5. So it's going to load a 5, then it's going to decrement the 5. It will make it 4. Then maybe the consumer may get interrupted at this point. And then the CPU is given to the producer. And the producer at this point will look at memory. Well, it will just store the value of 6 into memory, so it will store 6 into counter. Then the consumer will eventually get the CPU, and it will store the 4 into memory. Now, is 4 the right answer here? What's the right answer? 5. Because we have an incrementation and a decrementation. And we expect one of them to happen before the other. Right? So if all the instructions in blue, the producer instructions, get executed before the instructions in yellow, then we will get the expected result. But there is no guarantee that this will be the case. In fact, there is another possibility, which is what?
Ends up being 6
How will we end up with 6?
if the green goes first and it gets interrupted with the blue.
Yes, if we basically swap them, or if we just swap the last two. If the last two happen in the other order, so if the consumer keeps the CPU for one more instruction, so if this happens before this, then we will end up with 6. So there are 3 possible answers here, 5, 6, and 4, and it all depends on how scheduling happens, and it's something that we do not control. So we need a synchronization method that will ensure that we will get the right answer, regardless of what happens in the system. Under all conditions, we want to get the right answer. We don't want to be, in this situation where multiple answers are possible. And this is, by the way, that's why parallel programs are hard to debug, because if you rerun this multiple times, sometimes you'll get 5, sometimes you'll get 6, sometimes you'll get 4. You just repeat the same thing, depending on how these 6 instructions will get interleaved. So these are 6 instructions that we are interleaving. It depends on how they will end up getting interleaved. You may get different answers. By the way, how many people have noticed in assignment 1 that if you rerun the producer and consumer program, you will get different interleavings? So how many people noticed that? The interleave, yeah, so at least one person noticed that. So if you haven't, go and experiment with this, run your producer-consumer program multiple times, and then you will notice that you may get different results. By interleaving, I mean like producer produces item 1, then produces item 2, then consumer consumes 1, then consumer consumes 2, then producer produces 3. So this is one possible interleaving. But you may get something like producer produces 1, producer produces 2, producer produces 3, producer produces 4, then consumer consumes 1, consumer consumes 2, then producer produces 5. Many possible interleavings. As long as there is room in the buffer, the producer is going to write. And as long as there is something to consume, the consumer is going to consume. Okay, so this is what we call the critical section problem. So in this case, our critical section is the modification of this shared variable. So usually code that modifies a shared variable is a critical section that must be handled carefully. And how carefully should we handle it? We should handle it in a way that will ensure that only one problem can be in a critical section at any given point in time. So if modifying counter is in critical section, we want to make sure that only one process can be modifying counter at any given point in time. And if the consumer is modifying counter, we want to make sure that the producer is not allowed to touch counter until the consumer is done with its modification completely. Until it completes the modification of counter, then the producer or other processes that are accessing the same shared variable will be allowed to access. Okay, so this is what we call the critical section problem. So we will be studying multiple solutions to this problem. In fact, for this simple form of the problem, there is an easy solution that we will be discussing or will end up using. But there are more complicated synchronization problems than this. So this is the most fundamental synchronization problem. So with the critical section, we'd like to have an entry section where a process locks or reserves the critical section to prevent other processes from accessing that critical section while the current process is in the critical section, is modifying the shared variables. Then there is an exit section in which the process will release the lock, and then which will allow other processes to access the critical section. Then the remainder section is just the rest of the code that does not access shared variables and doesn't have any problems. Okay, so in the solutions that we will be studying for the critical section problem and for synchronization problems in general, there are three important conditions. One condition is mutual exclusion in the critical section. So we want only one process to be in the critical section at any given point in time. Want to make sure that we are making progress, that we are not in a deadlock. So if we are not making progress, then we are in a deadlock. So we want to make sure that there is no deadlock, and we want to make sure that waiting is bounded. If waiting is not bounded, bounded waiting. If waiting is not bounded, then we have starvation. So these concepts will become clearer when we look into specific examples. But bounded waiting means that if there is a process that is waiting to enter the critical section, there is a limit on the number of terms that other processes may get. It may get into the critical section while this process is waiting. So a process is guaranteed to wait for a finite or a limited number of other processes or other process accesses while it's waiting for the critical section. Now we will see that there are situations where this is not the case and where we will have starvation. So the waiting process may starve.